for this discussion. If you want them, they'll be Friday morning. But there's two notions we're talking about here. One is the abstract storage locations. These are virtual entities that can be used to store data. So a file is the most common example that everyone's used to. A file doesn't really exist in a physical or any kind of form. It's really just a representation that's created by transforming, sectors in a disk to make it look like a file, but it doesn't really exist anywhere. And there's many other examples. Any data structure we use in a programming language is essentially an abstraction. You're taking bytes in memory and you're grouping them into a 4-byte integer or an 8-byte integer or a floating point or some other larger abstract storage location that's being mapped to and transformed by some lower level primitive storage location. We also have abstract events, which are basically one high level abstract event which causes multiple lower level events to occur. So common example is I hit my button on the screen to change slides, and there should be events occurring below that. It's one event for me, but it's actually hundreds or thousands of lower level primitive implementation level events that are occurring. But from my perspective and standpoint, it's one event. And so basically we can define a history for abstract states and events as well, and this exists. Depending on what level of detail you want to get into, there are multiple levels of abstract events. So there's a user level events, there's implementation level events, which are programming language events that occurred, as well as the primitive ones. And depending on what software engineering model you used, there could be other layers of abstraction in a program itself. So as an example, before we had the representation of the single event at each time, now we have this notion of D1 and D2 as being these abstract data locations. E1 is an abstract event which writes to this abstract location D1 at a given time. But underlying all of these locations are these lower level storage locations and lower level events that are doing the actual reading and writing in this whole process. And so now we can actually start mapping the abstract state history and event history. And so the abstract state history basically maps a time, again, to some given state. In this time we have a subset, subscript x in here, which for now we'll just kind of assume this is the abstract states that can occur. Now to define this is actually pretty complicated, because the possible system states, the possible abstract system states, are based on the abstraction types that exist at that given time. Because an abstraction type exists only because a program creates it. So if the program doesn't exist to make that file, then the file doesn't really exist. So, a common example of this, this situation is someone emails you a WordPerfect file or some other file that you really don't have the program to interpret that data anymore. For all intents and purposes, the other storage locations and data structures and abstractions in the WordPerfect file don't exist to you because you don't have the program to properly interpret it. It's just another file to you. You can't actually store the author's name or change the paragraph settings or change the paragraph content because you don't understand that actual storage location. So to determine the possible states of the system at a given time, we have to know all the various programs and abstraction types that are supported at that given time. And to do that, we need to basically determine the possible states each time and then which programs existed to build up our set Q sub x. And this is actually a very hard problem in terms of, this basically requires analyzing every program on the system, which we don't do in practice because it's way too time intensive and very complicated and error prone. So in practice, this is one of these cases where a lot of assumptions are actually made from the actual theory of this. Similarly, we have the abstract event history, which maps a time to the abstract event that was occurring at that time frame. And again, we have similar problems, where the abstract events only occur because of what programs exist. So we have to analyze the programs to find out what events could occur and analyze them, which again involves some form of static or dynamic analysis. And again, it's a relatively hard problem. And in general, many assumptions are made about this process in practice about what events could have occurred or did occur. So in summary of this process, the abstract history, the process is basically to define the capabilities of each program on a system and then determine which state existed or which actually event occurred. All right. This is what I get for trying to add some sliding in there. So if we readdress our digital investigation definition, the process is we basically start with one or more known states, and then we try to determine the rest. So if we look at our primitive state history, for example, the typical process is you get a hard disk from the suspect, you make a copy of it, and you import it in your tool. Basically what we're doing is we're starting off with one known state, one known primitive state of the system, and then we try to determine what the abstract states are, what the previous primitive states were. We try and fill in all these parts of the history that we don't know. And these are generally inferred histories because we only have one state in time, and we make inferences about what occurred, about what files occurred in the system, about what deleted files were, what files that are now deleted, what they were before. We try and make inferences about previous states in the system. But there's one problem with this concept, and the problem is that what are known states when it comes to a computer? And how do we actually know anything about anything? This is kind of one of these philosophical discussions which we're not going to quite get into about how do we know what we know and all of these various things. But in general, we're taking the assumption with these things that we know what we can observe. And I know that I'm wearing a green shirt because I can observe that this color is green. And in the past, I've been correct with the assumption that when I thought it's been green, it's actually been green. Now, if I'm colorblind, we get into some problems here. But it's an assumption that if someone's telling me I'm wearing a pink shirt, I'm going to believe my observation over someone else's because it's actually a direct observation that I'm observing directly. Whereas an indirect observation is something someone else tells me. So someone can tell me what someone else is wearing. I may or may not believe it depending on if I trust that person or if I have contradicting evidence. And the main point of this basically is that any indirect observation is a hypothesis. That it's not a fact. We can usually assume that what we directly observe is fact, but that indirect observations are hypotheses that we may or may not test to certain degrees depending on how much we trust the source of this information. The problem with this, going back to digital investigations and digital forensics, is that everything about digital states is indirect. There is no way that I can directly observe the state of a computer without using tools and hardware. I can open up a disk and look at the platters, but I can't actually recognize the actual value in those platters until I use hardware or software to help me in this process. And therefore, everything's an indirect observation and a hypothesis. Which brings us back to the original definition I gave of that the investigation process formulates hypotheses about states and events because we actually never know anything for a fact. So with this model, and we can actually, in the thesis and all these things, we can prove that this model represents all of the states and events that occurred in the system at the primitive abstract level. So we have some kind of proof of completeness of this. We get into, all right, now how do we actually apply this model to actual usage? And this gets into the actual main topic of this talk, which is the analysis categories. And based on the history model variables, which we kind of glossed over in this discussion, we can define different categories of analysis techniques. And they're basically broken down into 8 categories. As we'll see later, they're kind of arbitrary. But the point is we can show completeness in that each category defines certain variables. You can organize them into 4 if you want to, 1 category, 12 categories. It doesn't matter as long as they define the specific variables in the actual history model. And then each category has 1 or more classes that can be used to define these variables. And we define some of them here based on what's in practice, just the basic design of the